Hello, this is Marvin Pirito, and I will be discussing number 4, criteria for measuring and comparing urban structure by Bourne, 1982. So, it is useful to have a set of criteria that would help measure and compare urban form and spatial structure. But what is urban form or forms? So, it is the physical characteristics that make up built-up areas. This includes the shape, size, density, and configuration of settlements, while the spatial structure, on the other hand, is a term used to denote and discuss the distribution of activity within a metropolitan area. The sets of criteria brings together diverse concepts for evaluation purposes. So this we will provide 20 criteria grouped into 4 sections. Most of the criteria are self-explanatory in both intent and applications. The first level of criteria is called context. The first section suggests that the internal structure of urban areas will differ if the building, stock, the street system, and industrial plant are of different ages and constructed under differing policy, technology, and economic conditions. We have here timing, the time and stage of development, functional character, predominant mode and type of production. That's the function, so example would be service centers, mining town. Next is the external environment, the socio-economic and cultural environment in which the city is embedded. Number 4 is the relative location, position within larger urban system or the core periphery contrasts. The next level is called macroform. The second set of criteria consists of the more traditional and widely known indices. For example, cities of more or less similar population located on different topographical sites will each produce different urban form and even their transportation system may differ. So ang pasabot ani bisag kung sa kaparihang ilang mga tao nga nagproduce sa usa ka lugar, kuan jud di jud magkaparihang ilang urban form and even their transportation system may differ. So this set of criteria, the macro form, pasabot ni Rena, traditional and widely known indices. Tungod kay nabilong dire is the scale, which is the size or in area, population, economic base, income, etc. Ang shape, the geographical shape of the area, the site and topographic base, so the physical landscape on which the city is built. And lastly, the transport network, the type of configuration of transportation system. Kay lahi jud ang mga sakyanan kung kuan bukid ang imong lugar diya ang uban sa city imong ikumpara kuan jud kanang kasagaran dito is mga vehicles na nga di makina, so di jud magkaparihang ilang transportation system. So this is the third level in which we will call internal form and function. So the third set of criteria relates to indices of urban patterning that are easily measured. Combined, these indices provide a relatively comprehensive picture of the geometry of the city, but very little is known about the operation or behavior of the city itself. So the first is density. So the average density of development or the shape of density gradients. So this is the population density patterns po din. The second is the homogeneity. So the degree of mixing or the segregation of uses, activities, and social groups. 11 is the concentricity, the degree to which uses, activities, etc. are organized zonally about the city center. Next is sectorality, the degree to which uses, activities, etc. are organized sectorally about the city center. Then, connectivity, the degree to which nodes or sub-areas of the city are linked by networks of transportation, social interactions, etc. Directionality, the degree of elliptical orientation in interaction patterns. So, example is residential migration. The next is conformity, the degree of correspondence between function and form, and lastly the shape, the degree to which different urban forms developed for one function can be used for another. This is the last level of criteria, which is called organization and behavior. We have your organizational principles, the underlying mechanism of spatial sorting and integration, cybernetic properties, the extent of feedback, the sensitivity of form to change. Next is regulatory mechanisms, internal means of monitoring and control. Example would be zoning, building controls, and financial constraints. And lastly, goal orientation, the degree to which urban structure evolves toward a priority objectives. We have here number 5, some selected theories and topics. The theory of urban planning is connected with defining and understanding the contents, practices, and processes of planning. Theory is linked with practice and vice versa. For planners, this linkage is vital because planning, unlike other sciences, is a prescriptive or normative and not a descriptive activity. The planner's objective is not merely to describe the city and its components, but rather to propose ways in which they can be changed, hopefully for the better, by Catanese and Snyder in 1979. So in this session, the concept of accessibility is explained with the help of examples. Location theory and its applications to transportation are examined, and a short account of zoning is also included. So accessibility. The basic concept underlying the relationship between land use and transportation is accessibility. In its broadest context, accessibility refers to the ease of movement between places. Then, accessibility increases, either in terms of time or money, when movement becomes less costly. Also, the propensity for interaction increases as the movement decreases. This is by Blunden in 1971 and Blunden and Black in 1984. So we have here example number 1. Each node represents an activity center and each link represents travel times in minutes. So we have here nodes and nodes, and these are the links. Transportation improvements are implemented in each link that travel times are reduced. So we have here the parenthesis is when the transportation improvements are applied. So how do transportation improvements affect the activity centers? So here is the solution. The first figure represents the time in minutes when the transportation improvements are not yet implemented. But when it is implemented, this is the resulting minutes by each nodes or by each links. So the row sums are the accessibility measure for each node. Naturally, lower travel time means greater accessibility. In all cases, there is a reduction in travel time. So for A, 18%, B, 31%, C, 20%, and D is 25%. So it is apparent that activity center B has benefited the most, followed by D and A. So we have here example number 2. A downtown D is connected to arterials, to activity residential centers A, B, and C, and to one another with travel times shown on the links. The arterials become more and more congested with the result that travel times, which is in minutes, increase to new levels, and most of the commercial and business centers located downtown establish branch centers in A, B, and C. So which activity center is likely to prosper the most? What possible actions on a part of the city would improve the downtown? So similar to example number 1, we have the nodes and the links, but we have here a slight difference, which is the downtown. And here is the network for example number 2. the before and after. As you can see, downtown is connected to the nodes, but the travel times to the downtown increases because of congestion. So the solution would be activity centers A, B, and C are all likely to be equally benefited for the transportation improvement, as the difference between 43, 45, and 48% seems hardly significant. The downtown is certainly going to deteriorate rapidly. The possible ways in which it could be saved would be to reduce the travel time by improving the traffic flow on the arterials, or to implement a bus system that would compete with the travel time to activity centers. So makita na to da. And after, na-improve na ang travel time from each node, but travel time from each node to the downtown node increases. So personal accessibility is usually measured by counting the number of activity sites. They are also called opportunities available at a given distance from a person's home and factoring that number by the intervening distance. Accessibility measures can be calculated for specific types of opportunities, such as shopping or working. One such measure is given by a sub I is equal to the summation j o sub j times d sub j raised to the power of negative b. So A is accessibility of a person at I. O is the number of opportunities at distance d from the person's home. And D is some measure of separation between I and J. They can be travel time, travel cost, or just simply the distance. And B is a constant. So such an accessibility index is a measure of the number of potential destinations available to a person and how easily he or she can reach them. The accessibility of a place with respect to the other places in the city can be measured in a similar way, in which case A is the accessibility of zone I. We have here another example. Example number 3. A small city has 3 residential areas, R sub 1, R sub 2, and R sub 3, with 1,500, 2,000, and 2,500 workers and 2 employment zones, A sub 1 and A sub 2, with 2,000 and 4,000 job opportunities. Find the actual relative zonal accessibility of the residential areas, assuming that B is equal to 1. So this is the solution for example number 3. Our formula is A sub O is equal to the summation D times the A sub D divided by T sub OD raised to the power of B, where D is 1.1 and 2, O is 1, 2, and 3. A is the number of jobs in zone D, and T is T sub OD raised to the power of B is the travel time function. So for A sub 1, we have here 2000 divided by 10 plus 4000 divided by 12. We have 533. A sub O, with similar process, we have 730. And lastly, for A sub 3, we have 800, with a total of 2096. Our relative accessibility is, so ang A sub 1 divided by the total would be 0.25, A sub 2 is 0.35, A sub 3 is 0.4, so with a total of 1. Here the accessibility of everyone living in a particular zone is aggregated, and therefore there is no way of distinguishing among different groups of people within a zone, such as those with cars and those without cars. For example, the 1,500 workers living in zone R sub 1 are all assumed to own cars, and each zone A sub 1 is 10 minutes. A person's ability to reach also depends on mobility and also the transportation system that exists. The next topic after accessibility is 5.2, location theory. So location theory. Theories of the location of activities, particularly residential, were developed in the 1960s by several regional scientists. By drawing examples from agricultural land economics, it is possible to conceive the specific use of a parcel of land being a function of its distance from a market, assuming there is one market located at the center of the featureless field. So the specific use of the land at any location would depend on its bid rent, L. As per equation, L is equal to E times Q minus A minus E sub Fk, where E is the yield per unit land, P is the market price per unit of commodity at site, A is production cost per unit of commodity at site, F is the transportation cost per unit of distance, K is distance to market. Do note that K is the only variable, E sub Fk, the total transportation cost that increases with distance. At a certain distance, E times P minus A is equal to EFK. This is known as the zero rent margin. In this figure, we can see the resulting bid rent curves for three hypothetical commodities. So farmers will naturally select the crop whose probability is the highest for the location. So that would be the distance between M to X. So the bid rent curves for crops A and B intersect at distance X. Then it would also mean the most profitable area to grow crop A. So for crop B, C can be best grown between X and Y, and also Z. This is the three-dimensional view of the crop distribution, or the distribution of crops. So the closest to the marketplace, the higher the bid rent, and the farthest would be the lower. As for the middle, it is considered a residential district. Notice that residential use has the shallowest of the three lines, with individual households making choices that maximize their individual satisfaction. So, similar to figure number 1, the bid rent being highest when closest to the marketplace. Industrial and residential being represented by X and Y and Z respectively. So here we have example number 4. A concentric city with a single market at the center wants to produce 4 different crops A through D, whose characteristics are given in dollars. So which crop should be produced at what optimal distance from the city center and the distribution? So what implications does this theory have for transportation and city planning in the context of rent, housing cost, and distance from the city center? We have here category A, B, C, and D with price per unit site per unit, production cost per unit, net price per unit at site, and transportation cost per unit with its Bates relationship. So the links would be 120, 20, 100, 20, 100, 25, 75, 10, and so on. So the 4 equations represent crops A, B, C, and D, and equating them pairwise gives distances 2.308, 8.182, and 12.12 miles, representing the radii from the city center to which it is most profitable to grow crops A, C, and D, respectively. Note that crop B is obviously not profitable to grow. So the vertical axis represents the profit and the horizontal axis represents the distance. So from point 0 to 1, point 0 to this point, which is crop A, we will yield a profit of more than $75. But in crop B, the distance in units is is not profitable because with the distance being large, but the cost will also become larger. Well, while well at point C to D, we have here the cost, low cost, but and also low distance unit. It would also be profitable because the capital would would not be as large, and the profit would also be returned. So distance from where the market when profit is 0. So A is 5, B is 7.5, C is 10, and D is 12.12. The crop A should be grown from the center of the city to a distance of 2.303. Crop C should be grown from where A stops. So at point 2.303 to 8.182 ang C. Then D should be grown from where C stops. So 8.182 to as far as 12.12. Agree, the crop B should not be grown at all because it will not be as profitable to do so. Transportation cost is a major factor of concern. The farther away from the market a crop is grown, the more it takes to get the product to the market. According to rent theory, the rent or cost of land is inversely proportional to the distance of the land from the CBD. The last topic for number 5, the effects of zoning. Activities, people, and locations all interact in such a way that everybody wishes to maximize their locations. People have reasons for living where they do. Business and industries also have locational preferences. Locational preferences result in patterns of concentration. Land use planners regulate the compatibility of land use patterns through zoning and other regulations. An example will make these issues clear. Suppose that a small city has several parcels of land, each owned by a person who is free to sell the parcel to the highest bidder. So people able to purchase these parcels of land on the open market pay a price. This free market sale, however, may possibly result in incompatible land use. So an example would be one of the parcels of land being sold to a person who wants to establish a small factory that may be adjacent to a housing complex. To prevent any kind of nuisance, most communities enact zoning ordinances to regulate the use of land. So land values. A simple model of land value can be represented by a linear function as follows. So land value I is equal to A minus B D sub I, where land value LV is land value, D is the distance from the CBD, and A and B are constants. A somewhat more elaborate model can be represented by a power function as follows. So land value is equal to A times D sub I raised to the power of negative B, where land value decreases at a decreasing rate. In both these models, the unknowns can be determined by least square or regression analysis. Models of land value for metropolitan areas can be quite complicated. For instance, a conceptual model for a large city located near the ocean could have an equation such as land value is equal to A minus B sub I sub times C sub I minus B sub 2 times M sub I minus B sub 3 times E sub I minus B sub 4 times S sub I, where LV is the land value at the site I, C sub I is the distance from the CBD, M sub I is the distance from the ocean, E sub I is the distance from the nearest elevated subway station, and S sub I is the distance from the nearest regional shopping center. Other models similar to the one described have used such variables as accessibility, amenities, and topographical features.